Yeah, welcome back everyone after this very, very long break. A short refreshment actually. So it's my pleasure to chair the second session of the tandemPV. I'm Michael Saliba from Stuttgart University, and we have a very special session with three speakers now. First with Mike McGehee from the University of Colorado and NREL, then Jinghuan Kuang from IMEC, and lastly Patricia Schulze from Fraunhofer ISE. And without further ado, let's jump right into the first talk with Mike McGehee, who's a very well-known person in organic photovoltaics, perovskite photovoltaics, and for tandems as well. And it will be our pleasure to hear him talk about module designs that will promote stability for perovskite tandems. Mike, the floor is all yours.
Thank you. Okay, can someone just confirm that you see my slides and you hear me?
It's perfect.
Great. Okay, well, this is what it looks like here in Boulder, Colorado. I thought it would be green by now, but we got snow overnight. Hope everyone is doing well wherever you are. Oh, I gotta get the slides to advance. Okay, so I'll just have one slide about the tandems that we described last year in science. Try to hit some of the highlights from what Caleb Boyd and Jishan Zhu did. We introduced a triple halide for the wide bandgap cell. We found that you can incorporate a substantial amount of chlorine if you have also used bromine and cesium to shrink the lattice. And then there's a lot of beneficial properties of having chlorine. It increases the carrier lifetime. I don't know if it necessarily directly prevents photo-induced phase segregation, but it allows you to get the target band gap with less bromine, and that certainly reduces photo-induced phase segregation. And so, yeah, using that, we were able to make a 27% efficient perovskite silicon tandem. It's been challenging to make the tandems even better during the pandemic. And so a lot of what I'm going to show today are things, modeling and stuff that we were able to do, even when the lab was shut down for a few months. So, yeah, I want to explore how we might make modules and how that can affect the stability. And you'll see how it has relevance specifically to tandems in several places. So when I look out in the perovskite community, it certainly seems like most people are planning or they actually are making modules with this classic design that involves 3 scribing steps. Maybe the only ones that seem to be planning to do it differently are those who are making the perovskite on silicon tandems. But there are going to be challenges here. It looks like no one is having trouble doing the actual laser scribing. However, it's hard to ablate and have on one side of the line the material leaving, and right on the other side, no thermal damage, especially if a beam has a Gaussian profile. And so a lot of times, on the side of the scribe line, there could be some lead iodide, which means the material is degraded to begin with. But I've seen, and I think a lot of people have probably also seen, that once you have lead iodide, it can further catalyze additional degradation. Not to mention, if I were asked to provide just one guideline on how to make these cells stable, I mean, there's more than one guideline, but arguably the most important is do not let metal touch the perovskites, because metals, will react with the halogens. And so if you have a via and you've got metal running right down through that, you have a lot of potential for reactions. And I'm not saying these problems can't be solved. People probably will find ways. But you know, in a 1 square meter panel with 100 cells, there's 100 meters of scribe lines, and whatever solutions are implemented, they need to work with very high yield, you know, at all of those places. And you know, as a reminder, I think a lot of the success that we've had with efficiency and stability was enabled by the work of Axel Palmstrom and Stacy Bent, who developed ways to use atomic layer deposition to put some tin oxide down, which then served as a buffer layer that allowed us to sputter a TCO. And these materials are less reactive with perovskites than metals, you know, even if halogens work their way up to them, and they're impermeable. And you know, we really like this impermeable layer up there, and it's quite a shame to make it and then take a laser and start cutting lines through it. And yes, you can still, you know, you can go package the whole solar cell, but I sure like having that impermeable electrode that not only carries current but also protects the solar cell. So I think it's at least worth exploring. Sorry. Exploring alternatives. And you know, here's an example. And when Jeremy Werner was in my group, he got really excited about this design. And if you have a metal substrate that is conductive, then you're able to run wire from the top of one solar cell underneath to the bottom of the other. So we call these singulated solar cells. This would be, you know, much more the way that a silicon panel is made, where a wire or a ribbon or something like that is running from the top of one cell, you know, to the other. And an attractive way to do this would be to use something like the Mia Sole Ultra wire. Here is an example of that, and I've had the pleasure of seeing how this is manufactured, and they literally have a spool of wire and a tool that very rapidly just winds it into all of these curves, and then it's embedded in plastic, and you can just simply stick it on top of one solar cell and then pop the other solar cell on top of the other side. And then when you go to laminate the package, it, you know, makes a really good contact everywhere. So I think this is something people ought to at least consider. If you didn't want to use the wire, you could also use the shingling architecture that some silicon solar cell companies do. And in this one, you have an electrically conductive adhesive, and you just put the top of one cell, sorry, the bottom of one cell right over the top edge of another cell. And if it's several centimeters across, you do need some metal grid lines, but in this architecture, you don't need full bus bars. You don't need metal ribbon running over. So these are a couple of ways that one might imagine making a module. And if we look at some of the advantages, binning can really improve the yield. You can take each one of these relatively small, they're not tiny, but relatively small solar cells, measure their efficiency. If there's a bad shunt, you can just throw that solar cell out, and you could bin solar cells of various efficiencies like most solar companies do. Whereas if you make a square meter or a 2 square meter panel with a monolithically integrated architecture, you're going to have to throw the whole thing out if there's one bad defect. And then, as I was saying earlier, you can build this impermeable electrode on the top, and you don't need to pierce it with laser scribing. You don't have a via, and so you don't have metal running down through the solar cell. You could build this on metal foil, which means you could build it, if it were a single junction or an all perovskite tandem, you could build it in a roll-to-roll coater. I still think you would probably use glass to encapsulate it or to package it later on. And then if you're using metal wire, the sheet resistance doesn't have to be outstanding for the TCO, so you can thin that down a little bit. And sputtering ITO is one of the more expensive processing steps in most thin film solar cells. I mean, to be fair, there are some disadvantages, and metal tends to be rougher than glass. And so it certainly could be challenging to build these solar cells on metal. To be clear, these are thought experiments. We've not yet made cells on metal foil. You're adding a sheet of metal and you're still using 2 sheets of glass. So there's some extra materials that could drive up materials costs. And while there may be no metal going down through the cell, there's now a metal substrate. And I think you would need an extremely good barrier between the solar cell and the metal foil. Or you would have to find some metal that is not reactive, and you can acquire it in large sheets. And then, Jeremy Werner made a tandem that could be on metal foil. Most all perovskite tandems start with a wide gap cell on glass, and then the narrow gap cell is made second. So we had to flip that order, and we have the low gap cell made first on the substrate, and then there's the wide gap cell. And we didn't have a lot of time to optimize this, but we were able to demonstrate 18%. And I don't really know of any reason why the tandems in this architecture couldn't be just as good as the ones where the order is flipped. Okay, so now I want to switch gears a little bit. Sorry for those of you who saw this part just yesterday at Michael Salaba's other conference. We do need to think about how panels are going to perform in real world conditions. And here's a photograph where you can see that in the winter, when the sun is low in the sky, one row of panels is shading another. And then quite often when snow melts, you have snow covering some of the cells and not others. And you can also have shadows from other things. And when you have these conditions, the illuminated solar cells are generating power, and they're trying to push current through the shaded solar cells, and all of the solar cells have to pass the same current. And what will happen with the power point tracker is that it will sweep around and it will find a voltage where the shaded cells get put into reverse bias so that they are able to match current with the illuminated cells. And unfortunately, most thin film cells tend to get damaged when they're put in reverse bias. To some extent, I'll say silicon panels avoid the problem by having bypass diodes, and they break the panel up into typically 4 strings. And if one string has a shaded cell, then that will get shut down, and the other strings can still generate power. And with cadmium telluride, they do have the problem. In other words, the cells do get damaged, but you would need a bypass diode for each solar cell, and it's too expensive. And so I don't think First Solar does it. Instead, they just have long, vertically oriented solar cells. And at least if snow builds up at the bottom, it covers all of the cells equally. And so none of the cells get put into reverse bias. But I also think that it is one of the reasons that they only put their panels in utility scale installations, where they can protect them from shading, and they can even make sure that the people who clean them don't cover just one solar cell. So anyway, motivated by this, we, with Luca and Jay and Isaac and Ross and Eli, we set out to study these solar cells in reverse bias. Actually, even before that crew, Andrea Bowring looked at the cells, and we studied a wide collection. You can look in the paper and see specifically which perovskites, and we use lots of electron transport layers, hole transport layers, metal and ITO electrodes, and we always saw substantial current starting somewhere between -1 and -4 volts. Now, in and of itself, that could be wonderful because that allows the cell to current match to the illuminated cells. And you might even argue that the lower the turn-on voltage, the better, because the power you're dumping is current times voltage. And so if the voltage is lower, you're not going to heat that cell up as much. Unfortunately, I would say we've found at least 5 degradation mechanisms in reverse bias. With metal, it's just astonishing how quickly the solar cells degrade. We believe metal punches all the way through the solar cell. If you use thermal imaging after you've operated the cell in reverse bias, you see very small hotspots, which is almost certainly where metal is going through the device. So pretty early on, we just stopped using metal, and you know, my group has always been a big believer in ITO electrodes anyway, for the reasons I said earlier. So we've studied those a lot, and now our protocol is a bit more advanced than just running an IV curve and reverse bias. We pick a reverse bias voltage, and then we'll hold it there for typically 30 seconds or a minute. And then we find that when we go back into forward bias, under light, the efficiency will be reduced, but we do find that a lot of it recovers. So a typical recovery protocol is a few minutes in the dark at 0.7 volts, and then a half hour under light. And then we remeasure the IV curve. And you'll see that for this particular solar cell, aging at -2 volts did not cause a problem. However, aging just briefly at -3 volts really substantially changed the IV curve. And introduced a lot of hysteresis. The dashed is the forward sweep, and solid is the reverse. And then you see -4 volts almost completely destroyed the solar cell. Here you see a summary of more data. The x-axis is the applied reverse bias. The blue curve is when we had that bias for just 1 minute, and orange is just 2 minutes. And you see that maybe not a whole lot happens but within -2 volts, but once you go past -2, the degradation is really pretty severe. I mean, this is over 10% loss in just 1 or 2 minutes. Altogether, the degradation is about 100,000 times faster than it is under 1 sun at the maximum power point. So to understand why these cells pass current and what causes the degradation, Luca Bertoluzzi used some drift diffusion modeling. The simulator itself is described in this Joule paper from a couple of years ago. And it's just a standard drift diffusion simulator with one thing that a lot of the software packages don't have, and that is that it can also handle the mobile ions that perovskites have. And let me walk you through the band diagram. We'll start with one at 0 volts, and we see that the energy bands are flat through most of the solar cell, precisely because the mobile ions have moved. I like to look at where the charge density is, and outside the cell we have some charge in the electrodes that normally would set up a built-in electric field, but then we have the vacancies move, and that leaves some space charge on this side and piles charge up on the other, and that internal charge cancels the built-in field in most of the device, and so almost all of the band bending is on the left near the electron transport layer. So then when we apply reverse bias, there's an even stronger field from the electrodes that needs to be screened. So there's even more band bending over here on the left. And at some point, the barrier through here is small enough that we can start having hole injection into the device. Once the holes are in, they see a very intense electric field, so they will drift away from that electrode. And then we know that the current density has to be the same everywhere through the device. And over here, where there's no electric field, it's going to have to be a diffusive current. And there can only be a diffusive current if the hole density versus position looks like this. It's going to, at steady state, holes are going to have to be piled up in the center, and then there's going to have to be a gradient to drive the holes over to the right side of the device. And now I want to talk about the implications of having all of those holes there. Luca calculates that the hole concentrations around 10 to the 12 per cubic centimeter in reverse bias, and that's about the same as it would be in forward bias under one sun. The big difference is that under one sun, there are also a lot of electrons, but in reverse bias, they're not. They don't get injected, and they are swept out. And so the hole to electron concentration ratio is dramatically higher in reverse bias. And the reason we think that's important goes back to this work from Joachim Meyer and Michael Gratzel, where they show that if you have halogens on the octahedral corners, they can be oxidized by holes, and then they become neutral, which means they're smaller. That allows them to go into the interstitial site. But when they hop to the interstitial site, that also creates a vacancy as well. And then with the interstitial and the vacancies, now the halogens can move around a lot, and we'll look at the implications of that soon. And so they had shown that that happens under light, and we believe that this equilibrium here is pushed even farther to the right in reverse bias because there aren't many electrons. And so, some of the consequences are that the interstitials are non-radiative recombination centers, and we believe that's why after reverse biasing, the efficiency is a bit lower. We do find that that part is mostly reversible, because when you go back to forward bias, and we think that's what's happening during the resting I was talking about, the interstitials and the vacancies, can annihilate and send the equilibrium back to the left. However, the solar cell could get pinned, because if its ability to reduce, or if its ability to produce current is lower, and it is, then it can't current match the other cells, even if the shading is taken away. And so still those other solar cells can put it into reverse bias. And then if it stays in reverse bias, then you've got all these interstitials and all these vacancies for a long period of time. And with highly mobile halogens, a lot of undesirable things can happen. And so, if interstitials pair up and form iodine, that can leave the solar cell. I think the reason the devices degrade so fast if there's a metal electrode is that the halogens go out and react with it. I think the halogens sometimes etch the metal. Ross Kerner at Princeton and NREL has shown some nice work there of how that can help release metal and bring it into the solar cell. And so if I think about what to do about this, unfortunately, you're going to have holes in the device, and if you have a shaded cell and it has to current match, it's just going to get pushed far enough into reverse bias for this to eventually happen. And I don't know how you could shut off an electrochemical reaction. But what you could do is have the highly impermeable contacts, really high quality tin oxide or ITO that will at least keep the halogens where they're supposed to be. If we can't engineer a solution inside the solar cell, then you have to go more to systems level solutions. And as I said earlier, with silicon, you can use bypass diodes, and you can get away with one bypass diode for, it depends on the silicon cell, but easily it could be as many as 21 solar cells, because the voltage is relatively low and the breakdown voltage is quite high. Unfortunately, perovskites, relatively speaking, generate a good voltage. I guess that part's good, but they have a pretty low breakdown voltage. And so, depending on specifically which cell you're talking about, you can only protect one or two solar cells with one bypass diode. And at a cost of 25 cents each, that would likely be prohibitive. But one thing that's kind of neat is when you make a perovskite silicon tandem, the breakdown strength is the sum of the two, and you can really take advantage of silicon's high breakdown strength, and then we think you could protect as many as 9 tandems with one bypass diode, and that could be feasible. And there's a lot of things you have to take into account when deciding perovskite silicon versus perovskite. But this is one that I think is in perovskite silicon's favor. And so just to wrap up, a good topic for this whole week is, well, I guess we're at tandemPV, so most of us are probably thinking tandems over one junction. And then there's the 3 families of tandems. And then there's a couple of major branches in module design, either singulated cells connected by metal or monolithically integrated. And when you think about these choices, I mean, there's the really obvious efficiency, stability, and cost. But I encourage people to think about some of the less obvious ones, that you can bin singulated cells, you can avoid scribe damage that way. And we also need to look at all these options and think about how the panels would handle partial shading, or do people think that this is not really such a big problem, and is the plan to put them in utility scale installations and just be very careful to protect them from shading. With that, I thank you all for attending, and look forward to your questions.
Thank you so much, Mike, for the great talk. With that, we are open to the audience for questions. So there's a first one already posted by Usama Raji, and he's asking, and also thank you on behalf of the audience, of course. It seems that perovskites have a rather low breakdown voltage, so bypass diodes are not quite efficient as a solution. Is there an alternative solution that can be adapted for these cells? Very fundamental criticism now.
Yeah, I mean, it is what it is. I mean, I hesitate this early to say that anything is impossible, but I am basically saying that using bypass diodes to protect each solar cell is, yeah, it's just not economically feasible. It's also very difficult to run the current all the way to the side of the panel through the bypass diode and back. So I mean, if we look at the thin film industry, they have the problem. Their solar cells do degrade and reverse bias, and they don't. None of them have found it cost effective to put in bypass diodes. You know, you could say, well, it must not be that big of a problem if they chose not to use bypass diodes. But what has happened to most thin film solar cell companies? I mean, the overwhelming majority of them did not make it. And I always, whenever I have the chance, I interview people who worked at those companies and ask them what went wrong and try to learn from them. And many of them have told me their company failed precisely because of this, this shading problem causing degradation. And then, yeah, First Solar only puts their stuff out in the field, and only their trained people go out and clean those panels. And so it could be that the take-home message here is perovskites, they're not going to be on roofs. They're going to be out in open fields. Or I issue the challenge. I mean, people could be clever and think of ways to keep these solar cells from going into reverse bias.
And let me squeeze in a last one by Rutger Stadtmann, who's saying, very nice talk. Thank you, Michael. As to your reverse bias consideration, would it make sense to take lateral inhomogeneity, that is local field electric enhancement, etc., into consideration for modules in addition to transversal, the 1D approach you presented? Certainly, when you get to using metal foils, such local effects can be killing defects or killer defects rather than the manageable surface roughness. I can also copy the question into the chat if you want.
Well, yeah. So, I mean, yeah, certainly, like in a silicon solar cell where there's been a lot more work on reverse bias, the breakdown voltages do vary, and the cells with lower breakdown voltages, yeah, frequently, yeah, there's a defect. That's exactly right. There's a spot where it's easier for current to flow, and yeah, here if the metal was rough and the solar cell was thinner in one place, it's not hard to imagine that you get more current there. And then of course that would make it hot, and you could easily get runaway degradation. So yeah, I certainly agree that lateral inhomogeneities would likely make these problems even worse. And I mean, dying in a minute is already pretty bad. So yes, it will just only get worse from there.
There's actually no time, but let me still ask one question by Klaus Ramsbeck. Very nice talk. There's a question regarding the reverse voltage of silicon perovskite tandems. Would you assume that an identical shading for both spectral parts would be guaranteed usually, or could it be that one of the two is shadowed more strongly than the other, possibly leading to the total voltage being applied to the weaker reverse behaving cells? I think that's interesting.
Yeah, I think that I mean, if you had a poorly designed tandem, you could imagine the situation where the current mismatch could be so bad that it could put one of the cells in reverse bias, but I don't think that would happen in a properly designed one. I think this would be more likely to happen in the lab, where you're using lasers and LED, where you deliberately try to excite one solar cell over the other. I don't think that would happen outside. you know, I don't think clouding would take it that far.
Okay. Yeah. Thank you so much, and thanks again on behalf of the audience. Fantastic talk. And unfortunately, we have, or fortunately for the next speaker, we have to move on. Thanks so much, Mike. So
thank you.
The next speaker would be Jinghuan Kwang from EMAC. Maybe you can already turn on your camera. Yeah, fantastic. Great to see you.
Yes, thank you, Michael. Yeah, I will share my screen soon.
Awesome, yeah. So Jinghuan is a group leader, a senior group leader at EMAC, and he'll be talking to us about a thermal evaporation assisted hybrid deposition of perovskite for single and multi-junction solar cells. So perfectly fitting into our topic today. So maybe if you can share your slides, that'd be great.
Yes, actually, can you see the slides now?
Very good. It's still not in the presenter mode though.
Yeah, I will do it in the present mode. Yes. Yeah, is it now in the presentation mode?
Yes, it's perfect. Thank you.
Okay. Yeah, thank you. So yeah, hello everyone. This is Jinghuan Kwang at IMEC. Actually, I'm not a group leader, but I'm a senior researcher and the project leader. Because actually, sorry for this last-minute exchange of the speaker, because Tom, due to some unforeseen circumstance, he cannot make to give the talk. So I will give the talk, and also the title is a little bit